Yeah. Okay. Okay, one more time. Hello, Rail Life. Welcome to our rail inspection and test innovation. Rail innovation. What's the name?
Test area. Rail innovation test area.
Hello, Rail Life. Welcome to our rail innovation and test area. This is our rail inspection and repair automated robot based on the Warthog Cleared Path platform. We are at Cranfield University in Bedfordshire. We are the Center for Life Engineering Management. We have run a number of projects in collaboration with Network Rail related with the automation of the rail inspection and repair task, as well as development of technologies for sensing of the rails. And today you're going to see a demonstration on how an autonomous vehicle can be used to inspect the track autonomously without the need for supervision and perform a mock-up of a maintenance task. So next, my colleague Masume will give you more information about the demonstration that you're going to see.
Hi everyone, the purpose of today's test is to demonstrate the usability of the robotic system for railway track inspection and repair tasks. Actually, the main component of this robot is Warthog from ClearPath company. This robot has a number of sensors, including RTK GPS, 3D LiDAR, RGB camera, and an IMU and a velodometer that they are embedded in the body of the system. As you can see, at the front of the vehicle, a universal arm has been attached, and at the end of the arm, we have a rest camera which will be used for defect identification and close range inspection. This Warthog has been designed actually to run on the ground, but in order to make it run on the railway track, we have fabricated and designed a trolley in order to transform this Warthog into a rail vehicle. After shifting the vehicle onto the trolley, by the movement of the wheels of the Warthog, it will make it will make the trolley wheels to start moving. So in this way, the whole set will move on the railway track. Actually, we are not going to detect the real railway defect. Instead of that, we have a dummy defect, a QR code. And in order to show the capability of this robot to detect different kinds of defect, we are going to apply 3 types of QR codes. That these QR codes contains different messages. Based on the messages that are hidden in these QR codes, the arm will have different poses and different response. In this way, that it will actuate different poses and capture images from different angles. And in terms of the inspection task, you will see that first the vehicle is its initial location. Then by receiving the command, the arm will go to the straight pose, and then it will go to the inspection pose in a way that the camera at the end of the arm will capture the railway track, and then it will start moving. Often that the camera captured the defect on the railway track, it would stop, and the arm will actuate poses and then capture images from different angles. Now, my colleague will continue with the rest.
Hello, this is the camera view from Mufayan. The trolley is ready for the demonstration. It's moving on the track autonomously. The robot arm, the camera on the tip of the robot arm is inspecting the track. The robot is approaching the QR code. Now the camera detected the QR code, so the robot stopped. And the camera is capturing the QR code from different directions. After the detection, the robot can do some maintenance work autonomously.
Yes, so interesting. This robot is equipped with so much autonomous systems, and it's using ROS1 component to integrate all the sensors on board and to execute all the command task. For the LiDAR, it's good for obstacle avoidance, and we have the environmental camera as well to detect obstacles and detect the environment, cameras and pictures of people around. We also have the front depth camera to have close range. This was explained earlier by colleague Mezume. And interestingly, all the sensors goes into the ROS component, which is executed by the autonomous algorithm designed by one of our fantastic engineers here at Cranfield University. So I'll hand over a video.
Yeah, so now you present a video on how the LiDAR works for obstacle avoidance, and next there will be another video on positioning.
Okay, so now we show a demonstrated video of how the collision avoidance works and also the GPS positioning. Thank you.
Hello everyone, at Robot Life. I'm Jen Lee. I work on the software development for this robot. This is our latest railway robots and automated bench trolley. It has similar feature as the Warthog robot we talked before. The main difference is it's railway ready. It has the wheels ready to go on the railway track without any conversion. Today I'm going to show you an example of collision avoidance with the LiDAR sensor. Our LiDAR works by sending beams 360 degrees to the surrounding environment up to 200 meters, so it can have a clear view of what's around you. Today's demo, the robot will travel to the end by detecting this obstacle, which is the fake policeman, and eventually slow down. It will continue moving when the obstacle is cleared until reach the end. Now the robot start moving. Now the robot detects the obstacle and stop. The robot will stop unless the track is cleared. Now we clear the obstacle, the robot continue moving.
Hi everyone, my name is Masum Rahimi. I'm a PhD student at Cranfield University. My research was about developing and implementing autonomous localization and navigation for the robot inspection and repair system. This robot also equipped with a number of sensors, RGBD camera, 3D LiDAR, RTK GPS, and IMU and a wheel odometer. This vehicle has been considered to perform on and around the railway track. But considering the railway environment that is too complicated because of different reasons, GPS would degrade and it wouldn't work properly. So in this case, we need a fusion of sensor in order to improve the vehicle's location. This test is divided in two separate phases. The first phase, it is supposed that we have GPS. The vehicle starts moving in order to reach to the goal location. And in RVs, you can see that localization and mapping are running through RTAP map. And in RVs also, we can see a graph base that are generated from the RTAP map. In the related terminal, we can see that the GPS location has been reached. In the second scenario, it is supposed that we do not have any GPS. So this is the case that the vehicle need to identify where and when to stop in order to identify the defect location. Here, the vehicle starts moving and use the track side object as a reference point in order to specify the environments around the defect location and also improve the vehicle's location. Here we can see that by detecting the distance from the nearby objects, it starts publishing, and when it reaches to the defect location, the vehicle would stop.
Hello, Rob Live. This time I'm gonna show the same demo at RITA, but instead I will show a screen recording of the Warhawk machine. As you can see, this is a view of the camera on the arm. Now it's pointing itself to the side of the track. Look for defects, which will be represented by a QR code. Now approaching to the inspection point, start inspecting. There it is, a QR code we look for. Okay, QR code we look for. Now the arm is moving into different position to take a picture of the QR code. Now the arm go back to initial position, job finished.
Yes.
Yeah. I think the rope, oh yeah, it's finished. You just pretend that you didn't.
Yeah. Now this demonstration didn't fail at all. That was what we were expecting, 100%. So
It's because of the weather as well.
yeah.
It impacts.
So what we have seen is a demonstration how an autonomous vehicle and all the technologies around it can be used to perform the tasks that are usually performed by people on the rail track, which can be dangerous and also quite money consuming. So now we'll take a look at your comments and questions from the comment section, and we'll try to answer them. Thank you very much. No questions. We're finished.
I think it would be better to start the test or the demo earlier. I think 2:30 it's a bit late.
In June, probably.